All right, in this video, we're going to talk about the other form of Green's theorem, which is the flux/divergence form. The previous video, I covered Green's theorem in the circulation/tangential form. So make sure you check that out if you haven't already. So here we're looking at another way to calculate a line integral, which we've done before, where you want to measure the flux, or how much, for example, fluid is crossing over a boundary when you have a closed curve, which, as we did it when we did it as a line integral, we want to dot f, our vector field, with n, because that's a vector pointing straight outward across the curve, ds. That was sort of the theoretical formula for flux. We broke it down that if my field was made up of m and n, then it's the line integral of m dy minus n dx. And what Green's theorem says is another way to do this line integral is to do a double integral, integrate over the region R enclosed by our closed curve C, the partial of m with respect to x plus the partial of n with respect to y, which we call the divergence of f, or for short, div of f. And we'll talk about what that means. So this allows us to calculate the outward flux of a vector field across a curve C as the double integral of the divergence of f over the area of R. So let's see what's going on here. So a very similar picture for the explanation of why Green's theorem in the circulation form works. If I consider a small, tiny point, but we can look at it as a small rectangle, and we think about a field subject to a vector field, maybe a velocity field for a fluid, and we're measuring how much of this fluid, the velocity of that fluid, how much fluid is exiting the region. And here's our field m of xy, n of xy. So we'll take it in each side of the rectangle separately along the top. Because this is infinitely small, I can evaluate my vector field at any point. I'm going to use this one here. And since we want to do the exit rate, we want to dot it with a vector that is going directly outward, our normal vector, which in this case would be j, which is the vector 0, 1, times that by delta x, that's the length of the interval. So if this is your field f and you dot it with 0, 1, you can see that m is not going to be a part in it. It's just going to be n. So this would come out to be n evaluated at x, y plus delta y times delta x. If I go along the bottom, I'm going to evaluate my field at x, y. I would be dotting that with a vector going perpendicular. That would be negative j. So f of x, y dotted with negative j times that interval length would be, again, 0, negative 1, so it's just going to involve n. It's going to be minus n of x comma y delta x. Along the right-hand side, you've got some field here. That's f. We're going to dot it with our unit vector going outward, which is I, which is the vector 1, 0. So if I dot m, n with 1, 0, it's just going to be m. And I'm going to evaluate that at x plus delta x comma y. Whoops. X plus delta x comma y, there we go. Times this whole width, which is dy, delta y. Dotted with I, there we go. I already did that. Okay, so times delta y. And then finally, we're going to take the field and dot it with negative I, and that's going to give me negative m of xy times delta y. If I add up the total flux across all of the boundaries, if we do the top and bottom, add these together, I'm going to get n of x comma y plus delta y minus n of xy times delta x. Same trick I did on the circulation example. This resembles a partial derivative, and sure enough, if I divide this by delta y, multiply by delta y, take a limit as delta y approaches 0. This, by definition, is my partial of n with respect to y times delta y delta x. Similar along the right and the left, if I add those together, I'm going to get mx plus delta x, comma y, that should be a comma, minus m of xy times delta y, divide both sides by delta x, compensate with a delta x, take a limit. And this is your formula for the partial of m with respect to x. And so the total flux across the boundary, and this is what leads to our formula, if I add these together, both have a delta y delta x, it's the partial of m with respect, doesn't matter which order we add them. So I'm going to put the partial of m with respect to x plus the partial of n with respect to y. That's the total flux across the boundary of the rectangle. And if I want to reduce it down to an infinitely small point, if I divide by the area of the rectangle, which is delta y delta x, I'm just going to be left with partial of m with respect to x plus the partial of n with respect to y. And again, that's in our Green's formula. That's what we're going to be integrating. That's the divergence of f, or the flux density. That's a measure at every single point in our region, what the flux is. How you can think about that at a point, if you think about a gas expanding or maybe contracting at a point. So here's a point. If the gas is expanding, you can think of it generating a field that's moving outward, and the divergence of f at that point would be positive. So positive divergence or positive flux is moving away out across the boundary. If I had some kind of small boundary in here, it would be crossing outwards. Conversely, if I had a gas that was compressing, you had like a small boundary right here, then fluid or gas would be crossing into your boundary. And that would indicate a negative divergence at that point or along in that area. Sometimes you can call these a source because it kind of, if you're familiar with a source of water, like a natural spring, water's bubbling up off the ground and you get more fluid going outward versus a sink, when you can think of like fluid crossing over the boundary, going inward and draining into that point. So just some terms to help visualize what's going on. Okay, next step, now that we know what flux density is, divergence at a point, very, very similar picture to what we did with circulation. What if I had a closed curve C, where I've got some field and I want to calculate the flux, how much of the field, or if the field represents fluid, how much fluid is crossing over this boundary. We can talk about the region enclosed by the curve C. And if you think about the flux at every single microscopic point in there, the flux is coming outward, or we'll assume that, doesn't matter if it's coming inward. But if the same thing's true at the next point, notice this one's pointing to the left, this one's pointing to the right, they're going to cancel each other out. Same thing here. This one's pointing to the left, this one's pointing to the right. They're going to cancel out. This one's pointing down, this one's pointing up. They're going to cancel out. So at any two adjacent points, they're all going to cancel out. It's like pushing against each other, except for points that are right along the boundary. You would have stuff coming outward this way, which is going to get canceled out. But right here, if you have some flux going outward, that would not cancel out. Same thing here. So what it comes down to is just, if we integrate every single point in this region, it's going to work because all of the points on the interior are going to cancel out in terms of flux, and we're going to just be essentially just adding the flux up at every point along the curve, which is the equivalent to finding the flux as a line integral along the curve. So it's pretty clever. So let's do a couple examples. I use this same field and curve when I did a circulation problem on the previous video. So let's calculate the flux along, this is a unit circle here. So we have that's our curve C. Remember the parameterization for a unit circle, R of t would be cosine t sine t from 0 to 2 pi. So if we do this as a line integral, there's my m, there's my n, that's my x, that's my y. As a line integral, the flux using our previous formula is the line integral of m dy minus n dx. So going around the curve, we would integrate from 0 to 2 pi. M is x minus y, so it's cosine minus sine. dy, derivative of sine is cosine t, minus n, which is x, which is cosine, times dx, which is negative sine t dt. If I distribute this, I get cosine squared t minus sine t cosine t, and looks like we have another minus sine t cosine t. So if this isn't going to cancel out, and I might as well do it right now, remember to integrate cosine squared. This is a 21b thing. You want to use the half angle identity. That's 1/2 cosine, I wrote it backwards, cosine of 2t plus 1, same thing. Usually I write it as 1 plus cosine of 2t. I could combine those to make that minus 2 sine t cosine t. We could, if I distribute this, 1/2 cosine of 2t is going to integrate to 1/2 sine of 2t times another 1/2, so that'll be 1/4 sine of 2t. This is really 1/2, so that'll be plus 1/2 t. I could imagine a little u substitution. If that was u, there's du. So this is just the integral of negative 2u du, which is just going to be negative u squared, or negative sine squared. If I plug in 2 pi, this is going to turn into 1/4 sine of 4 pi plus half of 2 pi, which is pi. And if I plug in 0, I get sine of 0, 0, 0, all of those are 0. And actually sine of 2 pi is 0 and sine of 4 pi is 0, so I get an answer of pi. Now let's try that same integral. That was, I went through it pretty quick, but you know, you got to remember this trig identity. You got to do sort of 2 separate integrals. This one's a u substitution. With Green's theorem, this will most likely be a lot easier. Because Green's theorem says I can integrate this same field, which was x minus y, comma, x, over this circle, which had a radius of 1, was the unit circle, by integrating over the region the partial of m with respect to x plus the partial of n with respect to y. Partial of m with respect to x is 1. Partial of n with respect to y is 0. And this literally, since that's just one, that literally represents just the area of this circle, which is a circle with a radius of 1. So it's just pi times 1 squared, or pi. Same answer, much, much simpler. By the way, for this particular field, in the last video, I encouraged you to, if you can, or have the time, to try to sketch out the vector field, or use a computer to get a sketch of it and try to imagine what you've just found here. What this says, this was the same field from the previous video. Remember, flux is the tendency for fluid to cross over the boundary. Definitely there's a lot of circulation with this field, but there is stuff crossing over the boundary, right? The fact that my answer was positive pi means there is more fluid coming out, crossing over that boundary outward than inward. So in that sense, our answer of positive pi makes sense. And then one more example. Again, this one really highlights why Green's theorem can be so valuable. Because if I wanted to calculate the flux of this field across this curve, which is really made up of 3 curves, curve 1, y equals 0, curve 2, x equals 3, and then all the way back down, y equals x as curve 3, you would have to do 3 separate line integrals to calculate the flux. But using Green's theorem, it's going to be very much more simple than that. So we want to integrate over the region. Flux density, remember the idea is that every single point in this region, we're calculating the divergence, the flux density, which is the partial of m with respect to x plus the partial of n with respect to y. This is m, this is n. Partial of m with respect to x is negative 2x. And with respect to y is 2y. You can describe this region using vertical or horizontal cross sections. I think I'll just go vertical. So we'll go dy dx. Every vertical cross section on the top hits y equals x, bottom y equals 0, which is true as long as x is between 0 and 3. So this should be pretty straightforward to evaluate. Antiderivative with respect to y. X is constant, so negative 2xy plus y squared. If I plug in x, I'm going to get negative 2x squared plus x squared minus 0. So this is really just negative x squared. From 0 to 3. Negative x cubed over 3. And that gives me an answer of negative 27, negative 9 minus 0, so negative 9. Now, unfortunately, I didn't sketch out the vector field for this, but the fact that the answer is negative, what that means is for this particular field, if it was a velocity field for some fluid, there's more fluid coming in, crossing over the boundary, coming inward into this region than outwards. More fluid coming into R. That's what this negative means. Then outward. All right, so there's flux using Green's theorem. Let me know if you have any questions. Bye.